Okay, so what we saw in the beginning of chapter 19, the lecture 1, was that the potential difference created by the battery is equal to the EMF from the chemical reactions inside the battery minus IR, right? Where I is the current and R is the little internal resistance that is inside the battery. And so because of this internal resistance, we don't get the entire potential difference, the entire EMF, we get a little less, right? So that's what we talked about in the beginning of the lecture. So now let's apply what we learned for this problem, this first problem, 19.1. So it's an example from the book. So what do we have here? We have a circuit in which we are trying to turn on this device. The resistance of this device is 65 ohms. And so how we would write that? Well, the idea is we have a certain battery that we are using to feed, to create a current that will let us turn on our device. Okay, so this is the device, resistance 65 ohms, and here is our battery. So the potential difference here is this difference between this high region where we have high potential VA minus this region where we have low potential VB. Now, so this potential difference of the battery is VA minus VB. The problem here is that they don't give us the value of this potential difference from the battery, which is what we use to feed our resistance. They give us instead, if you look at the problem, they give us the EMF and the internal resistance of the battery. So what they are giving us is what is inside here. All right, so that's why we have then this circuit where we have the EMF here. So here is a certain potential, I'm going to call it V1, and on the other side we have the VB, but then we have this internal resistance that give us a drop in the potential. So this little resistance R, which is given to us, is 0.5 ohms. So once the current goes through that, we have this drop, the potential becomes then VA. And then we are now in our circuit with the potential difference VA minus VB. All right, so all this inside here is the battery. Okay, all right, so let's see what the problem is asking us. Let's see the first question. So let's read the whole problem. We have this resistor, 65 ohms. Okay, that's what it is here, 65 ohms. Whose internal resistance is 0.5, so there we are, our 0.5, our little resistance here, and whose EMF is 12 volts. Okay, so as we know, the battery is not going to give us this whole thing, this whole 12 volts is going to give us a little less. So the question is now, calculate the current in this circuit. Okay, so I'm going to use what we've learned in the beginning of this chapter, which is this equation here, to try to obtain the current. The current is our unknown. So I'm going to use this equation plus what we also know, Ohm's law. Okay, so let's combine these two equations. What we have then is the V of the battery is the EMF minus IR. This IR is the little potential difference of this little resistance R. So this is what we know for the battery. We also know Ohm's law. Ohm's law tells us that the potential difference is I and the resistance of that big resistor of the big device we are trying to turn on. So these two equations we know. So let's combine them to get our current. So the potential difference of the battery is EMF minus IR. And according to Ohm's law, this potential difference of the battery is IR. Okay, so now we have everything. EMF is 12, I is our unknown, the little resistance is 0.5, I is our unknown, the big resistance is 65. We put all that and you can see that you will get 0.183 amps. So this is the answer for part A. All right, done. Let's see then part B. Part B is now asking, well, now that you have the current, what is the terminal voltage of the battery? What is this VA minus VB? And this VA minus VB that we wrote. Okay, now we have all the ingredients to get the potential difference of the battery. So there are two ways that we can do that. Either we go with the first equation, and the potential difference of the battery is our EMF minus IR. EMF is 12. Current, now we know, is 0.183, and little r is 0.5. If we do all that, we are going to get 11.9. This is the potential difference of the battery, what we actually get from this battery. And so you see that this is a little less than the potential difference that was created due to the chemical reaction. Okay, so it's a little less because we have that internal resistance. Another way to do that was by using the second equation that we have up there, the equation from Ohm's law, which is current I and big R. Again, this will give us the same result. 1.83, now multiplied by 65. This will also give us 11.9 volts. So that you have two ways to compute this potential difference of the battery. All right, now we come to the final question, question C. Let's see what is question C. The power dissipated in the resistor R, okay, our device, and the power dissipated in the battery's internal resistance, little r. Okay, so what is the power of each one? So remember, in the end of chapter 18, we talked about power. In the end of chapter 18, we were saying that how does a device work? We give to it electric energy, and it's going to transform into the kind of energy associated with that device. For example, if our device is a hair dryer, it's going to transform the energy, the electric energy, into thermal energy. Or if our device is a blender, it's going to transform the electric energy into kinetic energy, right? Okay, so associated with this transformation of energy, we can also talk about power. Now, what is power? Power is an idea that we already learned in chapter 6, where we said that power is energy or work, as we talked about in chapter 6, divided by time. In this case of devices, we said that associated with each device, we have the power of the device. Now it's how much energy per time that device needs to work, to behave as it's supposed to behave. Okay? And we said that we can compute the power of the energy that is transformed by time. And we found in that chapter 18 that this power is equal to current and potential difference. Okay, now this is one way of writing this equation. If we remember Ohm's law, now Ohm's law is potential difference is Ri. Using Ohm's law, we can also rewrite this equation to two different forms. Either power is equal to I squared R, or we can write it as power is equal to V squared over R. Okay, so these are three different ways to write power. Any of these three equations we can use to compute the power dissipated in each resistor. Now, in the resistor R, or in the little resistance, the internal little resistance of the battery. Any of the three. Now we can think about which one should be the most convenient. What do I mean by that? There is one quantity that is the same, that is constant for any of these resistances. And this quantity is the current. Why is that? Well, due to the potential difference, we'll have the flow of electrons. Then we'll have a current. The current that goes through the little resistance is the same current that will have to go through this resistor because it has no other path to go through. No? So the resistance, the current that goes through here is the current that is going to go through that. So that's a nice thing because we already computed this current, we know what it is, and we know it's the same for any of these two resistances. So a convenient equation to use, since we already know the currents and since it's the same for any of the two, is either this one or this one. Okay, let me start with this one. Okay, power is equal to I squared multiplied by R, by the resistance. Okay, so if I decide to use this equation here, I squared multiplied by R, let's then decide which R are we going to use, because the current we already said is the same, we have already computed, is 0.183 amps. Okay, so if I want to obtain the power dissipated by the resistor, by the device we are turning on, what are we going to put here? The current, 0.183 squared. And now comes the question, which resistance? Well, the resistance of that device, which is 65. Okay, you put these numbers in your calculator and you will get that this number is 2.18 watts because that's the unit for power. Okay, but you see that we thought about which resistance we should put that there. All right, so if now I want to obtain the power dissipated by the little resistance, what I'm going to use? Well, the current, because as we said, is the same for both resistances. No, it has only one path to go. But now comes the question, which resistance? Well, I'm going to put that little one because we are talking about the power of that little resistance. So here I'm going to put 0.5. And now I'm going to get a much smaller value since this is such a small resistance. And you will see we get something very close to 0.02 watts. Okay? All right. This is one way to solve this problem, and I think the most convenient and the most straightforward one. But you could say, oh no, I don't want to use this equation. I want to use the other one that we talked about. I want to use IV. Okay, let's use then IV. Current, as we said, is the same. We already know. Now let's be careful about the potential difference. The same way that in this problem here, we had to use the resistance of the device we are talking about, no? the resistor there, the internal resistance of the battery. Now we'll have to talk again about the potential difference of that entity that we are studying. So let's go again and write that circuit that we have. So here we have the EMF. We said that this is the potential V1, which as it goes through the resistance, it drops, becomes the potential VA. And then after that, it's the same everywhere. This is VA, this is VA, up to the point where we go through the big resistance, our device. Then we have another drop, it becomes VB. And then it is VB all the way back to the battery. All right? Okay, so if we want to use this equation here for our resistor, what is the V, what is the potential difference that we are going to use? We are going to use VA minus VB. This is the potential difference associated with this resistance. VA minus VB is the potential difference of the battery. Okay, so let me write this. If I want to compute the power dissipated by that big resistance, I'm going to use the current, which is 0.183, and now I'm going to put the potential difference of the battery. What was the potential difference of the battery? We computed that is 11.9. Okay, so you have to be careful about what is the V that we are going to enter here. In this case is 11.9, which is the potential difference of the battery, is the VA minus VB. This is the potential difference for this resistance here. All right, now that we did that, let's then try to compute the power dissipated by the little resistance. Which potential difference are we going to use now? It's not the potential difference of the battery, it's not the EMF. The EMF is this one. The EMF is V1 minus VB. It's not the potential difference of the battery. The potential difference of the battery is VA minus VB. What we need now is the potential difference associated with the little resistance, which is this VA is this part here, is this V1 minus VA. Okay, so the potential difference of the little resistance is that V1 minus VA. Is not the potential difference of the battery, is not the EMF. How do we get that? Well, you can use Ohm's law. Ohm's law tells us that this potential difference is the current going through that resistance multiplied by that little resistance. Okay, all right. So if we want to compute the power dissipated by the little resistance using this equation, careful with the V that you're going to put there. The current is 0.183. What is the potential difference? Careful, is the one across the little resistance. Okay, so you have to compute it from this IR. If you compute it, you will see that this is very close to 0.1 volts. Okay, so what you will have to put here, 0.183 multiplied by 0.1 volts, and that will give us that power dissipated, very close to 0.02 watts. Okay, so be very careful with this. What is the potential difference that we are going to use? Let me show to you another way to get this potential difference here, this potential difference for the little resistance. Another way to do that is from that equation that we already wrote. Potential difference of the battery is the EMF, minus the little VR. So we could also obtain the little VR from this equation. Now we saw that the battery is 11.9, the EMF is 12. That's why I said that the little potential difference across the little resistance is approximately 0.1 volts. Okay, very good. So that's the end of this problem.